Okay, so welcome everybody. This is intended to be kind of a self-contained lecture, and you'll see why in a second once I get into the nitty-gritty here, because the specifics of these calculations, of course, require paying close attention to the actual, form of the equation you're solving. So um, these methods are not really generally applicable, and it's kind of a lot of stuff to wade through, and so I didn't want to do it in a normal lecture. So this is for those of you who are interested in actually how these results were obtained. So the solution to a general cubic is due to Tartaglia and Cardano. So they both get credit for it because Tartaglia was the one who discovered this specific trick that allows this to be done. And Cardano was kind of the one that used this trick to take it all the way to the end. Cardano is also the first person in print to refer to imaginary numbers as actual solutions to these things. And so I believe the first recorded in an actual work computations with imaginary numbers are done by Cardano. And then a student of Cardano, Ferrari, was the one to solve the general quartic, okay, or fourth order equation. The reason why this is important is if we think back, right, even ancient Babylonians were able to solve both linear and quadratic equations. And so this kind of represented the first move beyond that to, the next higher order thing. And so since, ancient Babylonians were doing this, in say, 1500 to 1800 BC, and this was done in the 1500s AD, this is a gap of 3,000 years essentially where basically no progress algebraically was made on this. Now, I've mentioned previously that Omar Khayyam did some work and solved a specific class of cubics. So there was a little bit of intermediate work there. About 400 years before Tartaglia and Cardano, Omar Khayyam, solved this specific class of cubics. But the general solution wasn't done until the 1500s by these two. And so, as part of this thing that I mentioned, where Cardano was the first to deal with imaginary numbers, recall that. So I need some precursors, right? I need some maybe precursor statements. So first of all, recall that the imaginary unit I is defined to be the square root of -1. Now you might complain and say, oh, -1 doesn't have a square root. It doesn't have a real square root, but it has this symbol I, which we treat as its square root. And what we mean by that is I is this object such that I squared is equal to -1. Okay, now before you complain too much, and I'll talk about this a little bit later in the class, we come up with a symbol to kind of adjoin to the numbers we're already used to some new number that doesn't belong. So we did this with negative numbers, right? So you start out with maybe the counting numbers, right? The non-negative integers. So you start with 0, 1, 2, 3, 4. Of course, we know we didn't start with 0. That came later. But let's say that we have 0 now. So we have 0, 1, 2, 3, 4, 5, 6, and so on. Those are my non-negative integers. But of course, there are solutions, or there are equations, even linear equations in those non-negative integers that don't have solutions in non-negative integers, right? So x plus 1 is equal to 0, right? That has no solution in non-negative integers. That requires me to add in -1, right, to my number system. Okay, and then once I add in -1 and all of the algebraic properties it has to satisfy, that gives me all the rest of the negative integers, and so I get the integers. And so adding on in this way is exactly how we go from natural numbers to integers to rational numbers. Doing the real numbers, that requires us to do some Eudoxus tricks. Okay, but that gives us the real numbers. And then going from the real to the complex numbers is a similar thing. So I add in this symbol, I is the square root of -1. And so I'm not going to go over some basic arithmetic of complex numbers, but a general complex number is written as a plus bi, where a and b are real numbers. Okay, and this is a complex number. And so a and b are real numbers, I is the imaginary unit. This is how a general complex number looks like. We call a the real part and b the imaginary part. Okay, there's a one-to-one correspondence between numbers like this and the plane, right? So I could actually think of this as an ordered pair an ordered pair of real numbers, so that's associated to a point in the plane. I'm not going to do that here because that would come later. Tartaglia and Cardano didn't actually have that going on. That wasn't something until Descartes came up with this, Cartesian plane. This is not something they had access to, and so I'm not going to even mention that fact. Okay, so I need some basic facts here. So before I go further, I'm going to define omega to be minus 1/2 plus square root of 3 over 2 I. So I'm going to define omega to be this particular complex number. Okay. Going through some basic algebra of complex numbers, if I multiply omega by itself, so I have to FOIL that out using the fact that I squared is minus 1. What do I get? Well, omega squared is, it turns out, minus 1/2 minus root 3 over 2i. Okay. And so if I multiply these things together, I get the length of omega, what is called the length of omega, which is 1 in this case. Again, using this analogy with an ordered pair of points in the plane, you'll notice that these two coordinates are both on unit circle. And so this means that omega times omega squared, which is omega cubed, is equal to 1. Okay. If you have done any of this before, you'll quickly realize that omega is a cube root of unity. Okay, well, I'll mention this again here in a second, but that's where we're getting this omega. Okay, so the fact that omega solves this equation, z cubed is equal to 1, tells me that it is a cubed root of unity. What is a root of unity? A root of unity, so an nth root of unity is a solution to the complex equation z to the n is equal to 1. It's an nth root of 1. Okay. So, you might tend to think of 1 as having 2 square roots, right? And if I ask you what's the cubed root of 1, you would say, well, 1, right? That's the only one it has. But it turns out that if we're considering complex roots, then there are more. In fact, there are nth roots of unity in general. So there are 4 fourth roots of unity, 5 fifth roots of unity, and so on. Okay, so I'm not going to get too much into that. Just know that there's 3 cube roots of unity. Okay, and so I'll list out what those are here in a second. Okay, so what do I need? So I need some lemmas. So lemma 1, what does lemma 1 say? So lemma 1 says any complex number x plus iy can be written in polar form okay, which looks like r times cosine a plus I sine a. Okay, where r is a positive real number. Okay, and a is some real number. Okay. Now, the proof of this basically is to say, well, there's a point in the plane associated to this. Writing it in polar form is essentially you finding out an angle and a distance to be able to write that point as a point on some circle of radius r centered at the origin. Okay, that's the easiest way to show this. Lemma 2 is a consequence of what's called de Moivre's theorem. So we're not going to get there yet. So this is known as de Moivre's theorem. So this is that if I cube the polar form of this complex number, what I get is r cubed times cosine of 3a plus I sine of 3a. Okay, this is a special case of de Moivre's formula, and this actually works not just for 3, it works for n. So if this was n instead, this would be r to the n cosine of na plus I sine na. Okay. All right, and that can be shown with induction. It's not that bad. So the third thing, I need these first two lemmas in order to get the third thing. The equation z cubed equals 1 has exactly 3 solutions. Okay. The statement that it has exactly 3 solutions is a consequence of what's called the fundamental theorem of algebra, which I'm not going to mention anything more about just yet. What are the 3 solutions? The solutions are 1, we know that 1 works. Omega works, as we saw previously, and also omega squared works. Okay, so these are my 3 solutions. These are my third roots of unity. Okay, that's what this is referring to. Okay, lemma 4 says that if say W, now W looks a little bit too close to omega, so let's call it B. If B is any complex number that's not just 0, okay, then the equation z cubed equals B has exactly 3 solutions. And I can use my cubed roots of unity to know exactly what they are. So if I have found one solution, if z sub 1 is one solution, the other 2 are omega times z sub 1 and z sub 1 times omega squared. Okay, and the last lemma I need, if y and p are any complex numbers, then there are complex numbers, we'll call them u and v, such that y is equal to u plus v and u times v is equal to p. Okay. This is like the complex analog of the ancient Babylonian problem of finding such numbers, right? That have given sum and product. Okay. So, what is the idea? So I have these backing lemmas, okay, that I'm going to use here. So what is the main idea? So I start out with a general cubic. Now a general cubic is some degree 3 thing that has maybe leading coefficient that's not 1, but I go ahead and divide by that. Okay, and after I've divided by that, I have a general cubic equation. So general cubic What does that look like? That is x cubed plus ax squared plus bx plus c is equal to 0. Okay, that's what my general cubic looks like. So I'm trying to solve this thing. Now, a, b, and c are my coefficients, so a, b, and c are real numbers. Okay, these are my real coefficients. Okay, so starting with something that's completely general like this, it is hard to see what to do. Okay, it's very hard to see what happens here. Okay, and so this is why at this very first step, Omar Khayyam, for instance, his first idea was not to deal with something that's completely general like this, but to specify some specific, not specific numbers here, but a particular type of cubic, right? And see if that was something that could be dealt with a little easier. And so it turns out that, yeah, that could. So he found a way of doing that. But when this thing is totally general, it's kind of hard to see what to do. So here's where Tartaglia's trick comes in. So the idea is set x to be equal to y plus k, where k is some real number. Okay, so k is some real number here. If I do that, what do I get? I get y plus k cubed plus a times y plus k squared plus b times y plus k plus c is equal to 0. And now you're saying, well, how does this help? If anything, this makes it much, much worse, right? And it might look like that at first. It might seem like it makes it a lot worse. But the idea here is that I cube this thing. Okay, so I cube this thing out. Okay, and after I cube this thing out, I regroup the terms. Okay, and I only care about the cubic term of y that comes from cubing this thing out. I don't care about some of these other mixed terms that come from expanding this. All I care about is the term that's on y squared. So on y squared, we're going to have an ay squared. But what else do we get here from this expression? Right? What is my thing going to be? What's my coefficient going to be on y squared? Well, it's going to be, if you work this algebra out, it's going to be 3k plus a. We already knew it was going to be an a here, times y squared, plus I don't care what the rest of these things are. I don't care what multiplies y, and I don't care what multiplies, or what is the constant term. And you're going to see why that is. Okay, so I get some stuff here that I don't really care about the specific form, but I go ahead and do this, and then here's Tartaglia's trick. Set k to be equal to minus a over 3. Right, I said let k just be any general real number, but what if I make it minus a over 3? Okay, if I do that, it zeroes out this y squared term. That is exactly what I want to do. Okay, because solving a cubic equation that is missing its y squared, or is missing its squared term, its second order term, is something that is more doable. Okay, and so if I set k equals to minus a over 3, what do I get? That goes to 0, and so what I get is, if I go through this algebra, I get y cubed minus 3py minus 2q is equal to 0. Okay, so that's what I get just from here. So there's no y squared term. Now, where p and q are some real numbers, where do the 3 and 2 come from? Or minus 3 and minus 2? Purely from convenience. So you don't need to do it this way, but it's the algebra that follows is more convenient if you make this minus 3 and this minus 2. Okay, so minus 3, minus 2 are just for convenience. You can always do this. Okay. So this is the thing that we're actually going to solve. This is called the reduced cubic. Because we can always do this for any cubic. Okay, this is what we're going to solve. Now you might say, but wait, this is different than the one I started out with. True. But if you can solve this, you get a y that solves this. How do I get a solution to this original cubic? Well, x is y plus k. So once I've found this y, I take k, which is just my coefficient, right, minus a over 3, and then I add that to the solution I got here, and I get my solution to the original cubic. Okay, so if I can solve this, I'm done using that. Okay, so this is what we're going to solve here. Okay, all right, so what is the idea? So again, my reduced cubic looks like this. It's y cubed minus 3py minus 2q is equal to 0. Okay. So, idea is I set y equal to u plus v. Okay. If I do that, what do I get here? Well, I would get u plus v cubed minus 3p times u plus v minus 2q is equal to 0. Okay. So, how am I going to benefit here? The secondary idea, choose uv as in lemma 5. Okay, refresh your memory. Lemma 5 says that for any complex numbers, real numbers are also complex numbers, but for any complex numbers, there are complex numbers u and v such that y is u plus v and u times v is equal to p. Okay, so I can always choose u and v such that this works. Well, guess what y and p I'm going to take? I'm going to take y as the solution to this reduced cubic, and p is going to be this p here. That's why I've used p in that notation. Okay, so let's do that. Now, if y is u plus v here, if I cube this all out and expand here, what do I get? So I'm going to get, actually going through all this algebra, what do I get? I'm going to get u cubed plus v cubed. Remember your Pascal's triangle here, right? Plus 3uv plus 3u squared v plus 3uv squared here. Factoring that out, okay, from this term, what I get is plus 3 times uv minus p times u plus v minus 2q is equal to 0. Okay. So again, if you like, you can either expand this the old-fashioned way, or you can remember Pascal's triangle, which we haven't talked about in this class yet, but we're getting there. We're almost there, actually. Okay, and so we want to make this as simple as possible. Again, we're doing this thing, and you're like, why are we doing this? This makes it much more complicated than just the original reduced cubic. But not if we have chosen u and v as in this lemma 5, because if we choose u and v like this, what does that mean? Right? Recall, since we've chosen our u and v that satisfy lemma 5, that means that u times v is equal to p. Right? Which means that, for instance, v is equal to p over u. And I can plug that in here to make this a lot more simple. So if I do that, if I choose v is p over u, then here I get, in this term, I would get u times p over u. So that's p minus p, that's 0. That term goes away, right? So this term would go away, and I would be left with the much simpler expression u cubed plus v cubed minus 2q is equal to 0. Okay, or moving 2q to the other side, this is u cubed plus v cubed is equal to 2q. Okay, so now we're getting somewhere here. But if uv is equal to p, then uv cubed is equal to p cubed, or u cubed v cubed is equal to p cubed. Okay, and so now we again have this ancient Babylonian problem of trying to find two numbers with given sum and product. Right? Okay, so I have a sum of numbers, u cubed plus v cubed is equal to 2q, and I have a product of those same numbers, u cubed times v cubed is equal to p cubed. Okay, and so what do I get there? These two things combined tell me that u cubed and v cubed are solutions of the quadratic, which is t squared minus 2qt plus p cubed is equal to 0. Right? This was, in fact, the ancient Babylonian way that this quadratic came about, right? So that ancient Babylonian problem of finding two numbers that had given sum and given product gave rise to a quadratic, namely this one. Okay, so then we've taken the finding of solutions to a cubic, so this cubic then gets reduced to the problem of finding roots of quadratic. Okay, well, we know how to do this, right? And so we can do this using the quadratic formula, and of course it's very nice and simple for us. So how does this work? Let's write the roots of that quadratic, right? Well, we know that u cubed and v cubed are the roots, right? Thus, by the quadratic formula, what do I note? I note that u cubed is q plus square root of q squared minus p cubed, and v cubed is the conjugate root, right? It's q minus the square root of q squared minus p cubed. Okay. Thus, y, which we know is u plus v, is really u plus p over u, right? Where u is equal to the cubed root of q plus the square root of q squared minus p cubed. So we have found what y is. Thus, y is equal to u, which is this thing, which is really nasty. So cubed root of q plus square root of q squared minus p cubed plus p over that expression, cubed root of q plus square root of q squared minus p cubed. Okay, so this gives a solution to the reduced cubic here, but then an actual solution to the original equation would be given how? Well, to solve this original general cubic that I wanted to, I have to then add to this y k, which I've chosen to be minus a over 3. And so x, thus a solution to the general cubic is x, which is y plus minus a over 3. So that is that expression plus minus a over 3. And I don't think you're going to get anything out of me rewriting that entire expression. And so that's how I find a solution. To find the other solution, of course, I would need to consider the other solution of this quadratic, right? Now, there are cases here. And those cases are what we have to consider in order to be fully done here, right? So going back to this step, right, what is important is that I've written y in terms of p and u here. P is a real number. U is this cubed root of this quantity. Okay, and I need to consider the cases here, right? And so, so u is the cubed root of q plus the square root of q squared minus p cubed. Okay. Now, this is, we're going to use our lemma 4 here that we started out with. So by lemma 4, if u1 is one of these cube roots, so there should be 3 of these. If u1 is one of these cube roots, then the others are u1 times omega, that cube root of unity we defined. Okay, and the other one is u1 times omega squared. Okay. But if v1 is equal to p over u1, then u1 omega plus p over u1 omega, right? This is what y is supposed to be in this case. This is our y sub 1 here. What is this? Well, this is u1 omega plus v1 omega squared. And u1 omega squared plus p over u1 omega squared is equal to u1 omega squared plus v1 omega. So this gives all of them. Okay, thus my reduced cubic, which is y cubed minus 3py minus 2q is equal to 0, has roots, so it has 3 solutions. Those 3 solutions are u1 plus v1 as above. The next is u1 omega plus v1 omega squared, where omega is our cubed root of unity, and u1 omega squared plus v1 omega. All right, so there's my 3 possibilities. Okay. So these split into 3 cases. These 3 cases depend entirely on the sign of this, right? You might say that's a natural thing. So this is a natural thing because there's nothing wrong with taking the cube root of whatever. We don't care about that because q and p are real numbers. But taking the square root of this quantity is somewhat tricky because maybe that square root is not real, right? Maybe you're taking the square root of a negative number. And so this splits into three cases. So this splits into three cases. And the three cases are q squared minus p cubed is greater than 0. Q squared minus p cubed is equal to 0. And lastly, q squared minus p cubed is strictly less than 0. Right? Okay. And so, what do we get here, right, in each of these three cases? So, to deal with what this general form becomes, I'm going to quickly deal with these cases one by one. So, case 1. All right, so in this case, q squared minus p cubed is greater than 0. Okay. So say that q squared minus p cubed is equal to some r squared, where r is some positive real number. Okay. All right. Actually, it doesn't matter if r is positive or not. R is real. Okay. All right. So if u sub 1 is the real cube root, which we know exists in this case because, remember, we have u being the cubed root of q plus the square root of q squared minus p cubed. Right? So if u1 is the real cube root here, then, so it's the real cube root of, well, if q squared minus p cubed is r squared, then is the real cubed root of, say, q plus r here, right? Because what's underneath the cubed root here is q plus the square root of q squared minus p cubed, but if that's r squared, then that's just r. So this is q plus r here. Then v1 is the real cubed root of the conjugate thing, right? Q minus r. Right, recall the relationship between v cubed and this quantity here, right? I could have written v is equal to the cubed root of q minus the square root of q squared minus p cubed. Okay. All right, then the solutions to the reduced cubic are the real number u1 plus v1 and you get two complex or imaginary conjugates. So, and the conjugates u1 omega plus v1 omega squared and u1 omega squared plus v1 omega. Okay. And case 2, this is if q squared minus p cubed is equal to 0. Then in this case, if this goes away, then u is just the cubed root of q, right? u1 is the real cube root of q. Okay. And v1 is also the real cube root of q. All right, then I only have two solutions to my reduced cubic. Okay. My two solutions are 2u1 and minus u1. Okay. But this is a root of multiplicity 2, so the last one occurs twice. So I'm not going to get into a discussion of what it means for a root to have multiplicity greater than 1. So if you've never had that, if you've never heard that terminology, you can look that up, the multiplicity of a root of a polynomial. So this has multiplicity 2, this has multiplicity 1. So it's 3 roots, but this is a repeated root. Okay. So case 3 is kind of complicated, and I'll spare the details. Well, okay, it's not so bad. So q squared minus p cubed less than 0. What do I get here? So then in this case, what I get is that I'm going to write it like this. U cubed is q plus I times some real number r, and v cubed is q minus I times some real number r. So u cubed and v cubed are conjugates like this. Okay. Then u1, and so if I let u1 be a complex number a plus bi, with a and b real, then a squared plus b squared cubed is equal to q squared plus r squared, which is the same thing as p cubed. Okay, so a squared plus b squared is equal to p. Okay, and so v1 is a minus bi. Okay, which tells us that so u cubed and v cubed are conjugates, but actually it also turns out that u1 and v1 chosen this way also must be conjugates. Okay. So then what do the solutions look like? I get u1 plus v1, and I get, so u1 plus v1, and I get u1 omega plus v1 omega squared, and u1 omega squared plus v1 omega. These two things, so this one can be written as, turns out, minus a minus b root 3, and this can be written as minus a plus b root 3, where the a's and b's can actually be determined explicitly. So a is root p cosine of arctan of r over q all over 3. And b is similar. So b is root p sine of arctan of rq over 3 of r over q over 3. Okay. So kind of messy. But this is what the cases look like specifically. So to see what case 1 looks like, so Tartaglia and Cardano did not have access to this because they would have needed analytic geometry, which came later. But if you actually write, so if I let z be equal to this reduced cubic y cubed minus 3 py minus 2q. There are 3 cases here, basically 1, 2, or 3 roots. So case 1 was 1 real root and 2 complex, so it looks like that. Okay, so here's my y-axis, here's my z-axis if I'm defining it like this. Case 2 looks like this, so it's 2 roots, so two real roots. Looks like that. Here's my double root. All right, so here's my double root. Or repeated root, right? So it crosses once, and then this one's a double root. And then case 3, it crosses 3 times. So I get 3 roots here. Okay. All right. Okay. So that was the solution to the cubic. Now to finish up the quartic. So the quartic equation, this was done due to Ferrari, who is a student of Cardano's. It has, once we've divided the leading coefficient, it has form x to the 4th plus ax cubed plus b x squared plus cx plus d is equal to 0. Okay, so what we do here is we write this as x to the 4th plus ax cubed, and we put everything else on the other side. So minus b x squared minus cx minus d. Okay. So again, this is due to Ferrari. Okay, now what? Well, I want to try to complete a square term here, and I do this by adding a squared x squared over 4 to both sides. So once I've done that, what do I get? I get a squared looking term here. So I get x squared plus 1/2 ax, if you remember how to complete the square, squared is equal to 1/4 a squared minus b times x squared minus cx minus d. Okay, now I want to get a perfect square on both sides of the equation. So what do I add to both sides? I add t times x squared plus 1/2 ax. So I'm introducing a parameter t here because I want to figure out what I can add in order to get a perfect square. Plus 1/4 t squared, and I add that to both sides. So plus t times x squared plus 1/2 ax plus 1/4 t squared. So I'm adding this to both sides. When I do that, what do I get? So I get x squared plus 1/2 ax plus 1/2 t squared is equal to 1/4 a squared minus b plus t times x squared. That's what I get on the x squared term here from combining these. Plus minus c plus 1/2 at times x minus d plus 1/4 t squared. So here is the thing that I get. And I really want this to be a perfect square. Now, it turns out that if I have some quadratic thing, big A x squared plus big B x plus big C is equal to a perfect square. So this is a perfect square if and only if what? So when big B squared minus 4ac is equal to 0, i.e. b squared is equal to 4ac. Right? And so if a is not equal to 0 here, I can solve for c. In fact, if a is not equal to 0, this condition becomes c is equal to b squared over 4a. Okay, so if a is not equal to 0, this condition becomes b squared is equal to 4a. So then let's see. This is my a. This is my b, and this is my c constant term, right? And so this condition becomes the condition c, which is minus d plus 1/4 t squared. That's this. Is equal to b squared, that is minus c plus 1/2 a t squared, over 4 times a, which is 1/4 a squared minus b plus t. Okay, if we multiply all of this out, what do I get? I get a cubic equation, t cubed minus bt squared plus ac minus 4d times t plus 4bd minus a squared d minus c squared is equal to 0. So I can write that thing as a perfect square if I can solve this cubic for t. So what have I done? I have reduced me being able to neatly write out this quartic in terms of whether or not I can solve a cubic. Okay. So if I can find a t, and I'm always guaranteed to be able to do this, a cubic has always at least one real root. Okay. So a cubic always has at least one real root. But if I can solve this cubic for t, then what do I get? Then any, or a solution, I should say, to my original quartic, x to the fourth plus ax cubed plus bx squared plus cx plus d is equal to 0, can be done by, so this can be solved by finding a root of the equation that is quadratic, that is x squared plus 1/2 ax plus 1/2 t is equal to plus or minus the square root of big A x plus big B over 2 root A. Okay. Where does this come from? This comes from the fact that I can express this ax squared plus bx plus c. So long as a is not 0, I can actually write this as square root of ax plus b over 2 root a squared. Okay, so long as a is not 0, I can always do that. And so finding a way to turn my right hand or my left hand side here into a perfect square, I get a perfect square, and I take the square root of both sides of this equation. So if I square this, I take the square root of both sides of this equation, and I get plus or minus this thing squared. Yes. Oh, sorry. Yes, that's right. I think I've screwed up an exponent there. Oh no, that's fine. Yeah, that's fine. Yep, that's fine. That's all right. Okay. And so in that case, we've reduced solving the quartic to solving a cubic and then using that to solve this iterated quadratic thing. And so I get a bunch of nested radicals. Okay, and so you can see how nasty this becomes. The natural question was whether you could keep doing this pattern, right? Could you come up with a way of doing this for the quintic where you know, came up with some ingenious way of reducing a quintic to solving some particular quartic or something. And it turns out that you can't do that. It's impossible to do. But that wasn't known until the 1800s. Wouldn't be until much later that this was known. Okay, so anyway, I think I will stop there, and that's kind of the full exposition on how to solve the cubic and quartic. So hopefully you got something out of that. So anyway, I will see you all during next class.